Hello and welcome to this video. In this video, we're going to be going through the fundamental forces. So there are 4 fundamental forces that govern all interactions that happen in particle physics. And so what we're going to do in this video is go through them one by one and then come up with a summary at the end of the video on how we can compare them and notice which interaction is happening by which force. Okay, so let's start with a simple idea. So let's do a little bit of a thought experiment. We know that in a nucleus, right? So if I just take the nucleus of an atom like this, okay, I have multiple protons and neutrons. Okay. Now, a fundamental thing that we've been taught from when we're in like key stage 3 is that if we have two things that have the same charge, they'll repel each other, right? So if we put two positive things next to each other, they should repel each other. So if we put 2 or 3 positive things together, or even when we have really, really large atoms, we can put like 90 to 100 positively charged things, like almost like infinitesimally small distances between them. They should have a massive amount of repulsion, being able to basically cause the nucleus of this atom to explode, right? And it doesn't really make sense why we can have so many protons all very close to each other without the nucleus exploding. Surely these things should all be repelling each other. What is causing them to stay still? And most people will probably say, oh, we've got electrons in orbitals or electrons in energy levels that are controlling or like pushing it in. But then that wouldn't make sense either, because if we had electrons that are outside, the electrons and the protons are attracted to each other, so that would pull the protons further out of the nucleus, right? So there has to be some sort of force acting inside the nucleus to try and push everything together. And that is what we call the strong nuclear force. Okay, so the strong nuclear force is labeled because it is so strong. We can have 90 to 100 protons all basically right next to each other, and the strong nuclear force is still strong enough to overcome all of that repulsion and pull everything back together. Okay, so that's what the strong nuclear force does. Obviously, the strong nuclear force isn't acting on everything, because then it would be stronger than all repulsions, and then we'd never have repulsion ever. But we know we do have repulsion, and so it has to have some range. Okay, so the strong nuclear force, let's say it's responsible for holding the nucleus together. But it does have a range. Its range is between 0.5 to 3 femtometers. Now femto means 10 to the times 10 to the minus 15 meters, right? So this is ridiculously small, almost the size of just the nucleus across sorry, not the nucleus, the proton across, the radius of a proton is about 10 to the 15. So this can only happen specifically between 2 protons or 2 neutrons or something like that. What happens outside of these regions is what we would expect to happen. So if we get even closer than 0.5 femtometers to each other, then we get that repulsion, okay? Because at that distance, the strong nuclear force doesn't have an effective force there, and so it just reverts back to what we would expect it to be. Now there's a graph that goes along with this. Okay, so the graph is looks something like this, and it's a force against distance, okay, which I'm going to call D. Sometimes you'll see it written as R, R just meaning the radius away from the center point. It's probably more accurate to write it as R, so let's do that instead. Let's say it's r instead, but it just means distance still. Okay, so let's say this is 0.5 and this over here is 3. Okay, the shape that this force is going to have is going to come down from up here. It's going to cross the axis at 0.5 and it's going to come and level back up at 3 and go along that line. Okay, now there's a reason why we have this whole thing. Okay, so why is it when the force is less than 0, so when the force is negative, it's attractive, and when the force is positive, it's repulsive? Okay, so up here we have repulsive forces, and down here we have attractive forces. Okay, this idea is just a common convention in physics. Okay, so whenever we have any attractive force, we say it has a negative sign in front of it, because we know force is a vector, which means force can is dependent on its direction in a given direction. That's what vector means. And so for the force to be attracted to something, it's essentially moving it backwards towards the thing, is a way you could think about it. It's just convention. If we have an attractive force, it means we have a negative force. Okay, and so between 0.5 and 3 is where we get that negative force. That's where it's attractive. If we go any closer together than 0.5 femtometers, we get the two things will repel each other. Okay, so this is the basics of the strong nuclear force. This is in the topic of particle physics, so there has to be some sort of particle involved in transferring this force. And this is introducing a new thing now, which is called exchange particles. Okay, so I'm going to introduce what the idea of an exchange particle is. So an exchange particle is what we call a virtual particle, which basically mediates the force by traveling between two particles. Okay, so this is on a very small particle physics type scale. We actually have particles that mediate force. We're never going to have like a force that can act without a particle traveling between the two. Okay, what I mean by virtual particle is just that it exists for very, very short amounts of time. Okay, so virtual just meaning exists for very short time. Okay, now if you did more research onto this, you'd find that virtual particles are very strange things. Virtual particles can have momentum but no energy, which doesn't sound that profound when you first say it, but if you think about it, if it has momentum, it must be moving, and so if it's moving, it has to have kinetic energy, but it actually doesn't. So yeah, I'll leave that one with you, because I'm still mind boggled by it, as is most of the physics world. So virtual particles for A level, we're just going to say they exist for very short amounts of time. Okay. Each of the forces has a corresponding exchange particle. That is the particle that is created in an interaction spontaneously, that just travels between the two. And it's kind of just like, if you imagine it like a ball on a string, and there's a string attached to both of these particles. So let's say we had like two protons in the case of the strong force. We have two protons and they have a string connected between them, and there's just a ball that's traveling back and forth between them, and it's keeping them connected. It's like they're playing catch with the ball. And each of these particles is specific to the force that they have. For the strong nuclear force, the exchange particle that they have are called gluons. Okay, now gluons, the symbol is just small g, are massless particles, so they have no mass. and they specifically only travel between quarks. Okay, so that means if they only travel between quarks, the strong nuclear force only acts on quarks. Okay, meaning the strong nuclear force acts on protons, neutrons, baryons as a whole. It can act on mesons, it can act on single quarks, although we know we can't find a single quark by itself. It has to be in what we call a colorless system. But this is what we know about the strong nuclear force. So the key important things: we need to know the range, we need to know the exchange particle, gluons, we need to know this graph, we need to be able to recognize that this is what happens between this region. We need to know what it acts on, but there is a little bit of extra information here. So gluons act between the quarks. So this means that if we were to take a proton and then zoom in, we'd have 3 quarks, we'd have 2 ups and a down, and there'd constantly be gluons traveling in between these 3 things. Okay, this is the inside of a proton. Okay, now what's happening inside a proton and at this range is not gonna happen between 2 nucleons, between a proton and a proton. We can't have gluons because they don't exist for long enough times or long enough distances for us to be able to have that. So we need a secondary sort of exchange particle that's going to act between 2 nucleons. Okay, so this gluons act between quarks, but we also have pions. So if you remember pions, pions from mesons. So pions are mesons, but they act, they have mass, but they act between the nucleons. Okay, so the pions will travel between protons and neutrons, or protons and protons, or neutrons and neutrons inside the nucleus. So if we take a look at the nucleus now, and we had maybe proton, neutron, between these things we'd have a bunch of pions just traveling around. They'd go between all of these. Okay, so we have loads of pions traveling between all of them. And so technically we do have 2 exchange particles for the strong nuclear force. However, if they ask you to state the name of an exchange particle of the strong nuclear force, gluons are your safer bet, purely because they are the virtual ones that will exist for a very short amount of time. Pions we know can exist by themselves. They are just naturally formed in some interactions, and so we can't always go with gluons being, we can't always go with pions being the thing. So gluons is the safest bet because that's always true. Pions are not always acting as an exchange particle for the strong force, so just always go with gluons.